So hello everyone. So this is the second lecture in this course, and before we go into the details of operating systems, so this particular class we would provide an overview of the entire OS. So so this and then subsequent classes we'll look at the basics, some very important OS concepts, and the what the structure of an OS actually looks like, right? So just a quick reminder, in the last class we said that we had this slide which said that the main utilization, the main use of an OS is for two reasons. One is to provide hardware abstraction, so that nitty-gritty details about the hardware is abstracted from a programmer, right? So something simple as a printf, uh, to just essentially print something on the screen like hello world. The programmer does not need to know too many details about the hardware that is present and manage how this particular string gets printed on the screen. All the programmer needs to do is just invoke a function called printf, and magically the string hello world would be printed on the screen, right? The second use of the OS is as a resource management, and this basically is related to the fact that the amount of resources, especially the hardware resources present in the system, is limited, and there are multiple different applications that are executing on your system, and the operating system should ensure that this limited resources is effectively utilized among the different applications that is executing on the system. Okay. Now we also took this one example of 4 applications, app 1 to app 4, executing on a single operating system, right? We took this example of 4 applications, app 1 to app 4, executing on a single processor, right? Now the question here is about who or which application essentially executes on the processor at a given instant of time, right? So what we mean by this is that in order that application 1 executes, it needs to have instructions which are being executed on the processor. And since we have only one processor, so it means that only one application can execute at a given time, right? So what is the simplest way to solve this particular problem, right? The simplest way would be that we'd have the first application executing, and when it completes, the next application starts, executes for some time, and then completes, and the third application starts after that, and so on. In other words, we have each application, in other words, we have the applications executing in a sequential manner, right? But there are problems in this, right? The problems would occur when, let us say, we have one application which has a statement such as scanf, right? As many of you know, scanf is essentially a function in C which waits until the user enters something through the keyboard, right? So until the user essentially enters characters and presses enter, until then the application cannot continue to execute. So consider this fact that the application 1 executes for some time, it's executing various instructions, various functions, and so on, and then it lands on a particular function called the scanf. Now the application cannot execute, right, until the user essentially enters something, right? So we abstract this notion in terms of events. So when when app 1 reaches the scanf, we say that the system or this particular application is waiting for an event, and sometime later, it may be a few seconds later, it may be a minute later, it may be a few days later, the user could possibly enter on the screen, and then your system has essentially got the event, right? And the application can continue to execute, right? And during this particular period, from when the scanf function was invoked, that is when the computer started waiting for the event to occur, to when it essentially got the event, the CPU is idle, right? So now you see that there is a problem. Our previous scheme, where an application would execute until it completes and then the next application starts and so on, is not essentially good over here, right? Because we have multiple applications ready, that is app 2, app 3 and app 4 are essentially wanting to execute, but the CPU and the CPU is essentially doing nothing, that is the CPU is idle, but the other applications cannot execute because of the event, right? So this scheme of managing the CPU is not an efficient scheme, right? We need to find something better. So one of the solutions to this is the following, right? So, and this is where one of the solutions is the following, right? So the application 1 executes as before, and when it hits the scanf, it is waiting for an event, but now your operating system essentially kicks in and it knows that application 1 cannot execute further, right, until the event is obtained. So what it does is that it can now schedule application 2, application 3 and so on. Now when the event has been obtained at this particular point, then application 1 can continue its executing sometime later and complete its execution. So what you see over here is that we are not keeping the CPU idle, right? We are fully utilizing the CPU, and therefore this particular way of managing the resources is much more efficient than simply waiting for an application to complete executing and then starting the next one, right? So such a scheme is essentially called multiprogramming and supported in almost every operating system that is present. Okay, the critical point over here, the main takeaway here is that the aspect that of which application is waiting for an event and which application is ready to execute and can execute on the processor is done by the operating system. Okay, so does this solve our problem, right? So is this, of course, as we see, it is better than what we had previously, but is this the best that we can do? Okay, so let's see another limitation of this multiprogramming, right? Now let's say within say application 2, we have a statement such as this, which is while 1, right? And for those of you who have worked with C, you know that while 1 is essentially an infinite loop, right? And the processor is going to continuously keep looping or keep executing this loop infinitely. So now what you see is that app 1 executes for some time, it waits for an event, and then the operating system decides that application 2 executes, and application 2 hits the while loop and is continuously executing, leaving no chance for the other applications to execute and run on the processor. So what we see is that multiprogramming is not always the best, right? It's not the most optimized solution. It's not the best way to essentially handle the limited amount of CPU resources that is present on the computer, because of the fact that because of the fact that we have this one application, app 2, which is hogging the system, right? And many cases, if you have such a multiprogramming scheme, it would result in the system getting hung, right? In other words, we say that multiprogramming could cause starvation. So what do we mean by starvation here? We call starvation if we have applications like app 3 and app 4 which want to execute on the CPU but are not given the chance to execute, right? Application 3 and app 4 never get a chance to essentially execute, and therefore we say that these applications are essentially starved. Okay, so how do we solve this particular problem, right? So modern operating systems have a concept of multitasking, where your entire time is essentially split into what we call as time slices or time quanta, right? So this a time slice could be something as small as say a few microseconds to a milliseconds to a few milliseconds, right? So what happens over here is that periodically you would have you would have such time slices, and within the time slice the operating system would choose a particular application to execute. So in such a case, we would have, let's say, application 1 executing on the processor, it's running instructions and so on, and the app 1 continues to execute until it reaches the end of its time slice, right. So when the time slice completes, the operating system kicks in, and now it schedules another processor and another application, right, and app 2 in this case starts executing. It executes for a time slice, then app 3 executes for a particular time slice, right. So the OS and this is a feature of such multitasking operating systems, is that sometime later the operating system could schedule this application 1 to execute again, and app 1 would continue its execution from where it stopped, right. So so what it would mean is that app 1 executes for some time, it stops over here, and then sometime later the OS gives it another opportunity to execute, and it can continue its execution for another time slice. So your entire time on your computer is essentially split into such quanta, and each quanta is given to a particular application, right. So now if we, even if we have something like a while one, an endless loop that is present, it does not starve the other application, because the while one loop would only execute for a few quanta, say here for some time, and then subsequently for another time quanta and so on, right. Other applications like the app 3, app 4 and so on would also get their time slice and be permitted to execute on the CPU. In other words, these applications are not going to be starved, right. So there is no starvation, and thus a major performance improvement, right. Another very important thing, another very important aspect of multitasking is the fact that from a user's perspective, right, since each of these time slices are just a few milliseconds or microseconds, it looks like, or it feels like, you have multiple applications running in parallel, right. And this is what you essentially observe when you're using, let's say, your desktop or your laptop, right. So you open multiple windows, and it essentially feels like you have multiple of these applications running in parallel. Internally, what's actually happening is that the entire CPU time, the entire time of your system is being multiplexed across these various applications. Okay, so almost every operating system, that every popular operating system uses such kind of multitasking environment. In case that your processor has multiprocessors, in case that your system has multiple processors, what would essentially mean is that you don't have just a single processor, but you have multiple processing components, right. These could be multiple processor sockets, which is this, which is essentially an IC like this. So a socket essentially means that it's a single IC which essentially sits on your processor or is connected in your processor. Within a processor socket, you could have multiple processor cores, and within a processor core, you could have multiple hardware threads, right. Now, this is what a modern day high performance computer essentially looks like. Your regular desktops also would have at least one of these sockets with multiple processor cores, at least 4 or 8 such cores are present. Each core would have typically have around 2 or 4 threads, right. So your operating system should be able to handle such situations as well, right. So here, unlike what we've seen in the previous slide where there is just one processor present, here you have multiple processors, multiple threads that are present, and your OS should be able to handle such a scenario, right. So in such a case, if you have such multiprocessors or multiple processing units present in your system, the OS should be able to schedule applications across these various processors in an efficient manner, right. Now, there are a lot of consequences of having such multiple processors, and your operating system should be able to handle such situations, right. So, so here is an example of multiprocessors with multi-threading. Now, what we see over here is that on each processor core, you have time slices, and your OS decides which application should run in a time slice on a specific processor core, right. So, here for instance, we have two cores, and therefore, at any given instance, you could have two programs or two applications running in parallel. So, you have two application 2 and app 5 running in parallel. There's a there's a new time slice that starts at this particular instant, and then you have two other programs that are executing, right. And the OS should be able to efficiently handle such kind of scenarios as well. Now, when we have such kind of complex scenarios where you have multiple processors present, and each processor could have multiple threads present, and therefore you could have multiple programs running in a concurrent way, one thing that could actually occur is this concept of race conditions. So, what do we mean by this, right? So, let us say we have some resource, right. So, as an example, let us say that this is let us say a file that is stored on your hard disk, right, and you have two applications, say app 2 and app 5, that are trying to access or write to this particular file, right. Now, we could have a condition because you have these two applications and both are trying to use the same type of resource, right, that is your file. The end result is that it's not very deterministic what essentially or what eventually gets written on the file. Another example could be of a resource such as a printer, right. You have a printer connected to your system, and you have multiple applications which are trying to print to that single printer, right. Now you can imagine what would happen if two different applications, say app 2 and app 5, try to print documents or different documents to the printer, right. It could lead to catastrophe. Okay. So, such issues are called race conditions, and your operating system needs to find a way to synchronize or to share these resources in a way that application 2 and application 5 are synchronized, right, are able to utilize this resource in an efficient manner. One common way by which operating systems solve this problem is with the help of something known as synchronization. Right, synchronization is essentially a software primitive, and could be considered something like a lock, right. It is, yeah. So, if you have a resource and you associate that resource with a lock, it essentially means that at any given instant of time, you could have only one application which could use that particular resource, right. So, in order to synchronize this particular resource, okay, in order to synchronize between these two applications for this particular resource, the sequence of steps would be something like this, right. Application 2, or in this case application X, locks the resource, right. Now, when it locks the resource, it means that this particular application app 2 has complete control, or in other words exclusive control on the resource. So, the application 2 could utilize the resource. If it is a printer, then application 2 could essentially print its document. Now, if at any particular time during this thing, if application 5 tries to use the printer, then application 5 is blocked, right, until the printing is complete by application 2 and the lock is released, right. So, when the lock is released by a step known as unlock, then application 5 could lock the resource and utilize the resource. So, application 5 could then utilize the only then utilize the resource, and in our example could essentially perform the printing on the printer, right. In other words, what synchronization actually achieves is that at any given instant of time, there is only one application which can essentially utilize this particular resource. Okay, so another important aspect in operating systems is what we call as scheduling, right? So we've seen examples of this in the past in the context of time of multitasking. So here the idea is the operating system needs to find an efficient way to schedule various applications in a particular on the CPU, right? So let me repeat that. Um, the operating system needs to find an efficient way to schedule applications on the system, right? So yeah, so what could essentially go wrong over here, right? So the scheduling algorithm should be essentially should support various properties, like for instance, it should be able to be fair to various applications. It should not result in starvation. It should be able to prioritize some applications over the others. So what do we mean by this aspect of prioritize, right? So let's consider again this case of an automobile where we have three applications. Let's say an application which controls the car brakes, another application which controls the music player, and the third application which performs some offline drive analytics, right? We have these three applications which are executing at a time, and wants to each of these applications wants to execute on the CPU. So how do we prioritize? How does the OS decide which of these three applications should it essentially choose to execute on the CPU, right? So we clearly see that there are some priorities, right? So for example, the application which controls the car braking should get the highest priority because this is most time critical and is related to the safety of the car. While other aspects such as the drive analytics could be given the least priority because it does not affect the drive condition, the driving or the driver or the safety of the car, right? The music player could be given a priority which is between car brakes and drive analytics and the drive analytics software, because it's not as critical as the car braking software, but it's still important to execute the music player in a periodic manner, so that the music actually is played at a regular rate, right, which is expected of any music player. So here we have at the operating system which not just should manage these the CPU resource that is present, but should also be able to manage it in a way such that the requirements of the applications are essentially fulfilled, right? The car braking should be given the highest priority compared to the other two, right, in this particular example. Therefore here as we see, you would actually see that the car braking application is given, that is app 1 is given more priority and executes more often in this particular example than the other applications. Another requirement of an operating system is the need for isolation, right? So what does this mean? Now specifically when we want multiple applications that running on the system, we want one application to be isolated from the other, right? And this is required for two reasons. First, if you have something critical present in an application, so for instance you have an application like a browser which is which you have essentially connected to, say, your online bank account. So you want your username, password, your bank account details to be protected from let's say another application, let's say a gaming software, right? So for this you would want isolation between your web browser, which is connected to your bank, and the other applications like your gaming software or your text editor or anything else. The second requirement of isolation is to prevent a particular malfunctioning app to affect other applications. So if you have one bad app, like one dirty apple in your system which is executing, you don't want the effect to spread to the other applications, right? And in such a case, the OS essentially makes use of certain isolation techniques Yeah, to achieve this, the OS makes use of certain isolation techniques with the help of the hardware. So, in Intel processors, for instance, uh, uh, isolation is essentially present in multiple ways. So it is important for applications to be isolated from one another, and also for the operating system to be isolated from the applications. Why should the OS be isolated from the applications? Because if, for instance, you have an application which is malfunctioning, that app should not affect the should not cause the OS itself to malfunction, right? So there are multiple ways that operating systems, with the help of hardware, create such isolation entities. In Intel platforms, for instance, we have the concept of rings. So Intel's x86 processors, including the Pentium and the i7 or i9 processor as we see today, have typically have 4 rings. That is ring 0, ring 1, ring 2, and ring 3. So ring 0 is essentially the most privileged ring in which you have your privileged software like your operating system that are executing. Ring 3, on the other hand, is the least privileged, where you have your regular applications that are executing. So typically you would have ring 0 and ring 3 that are being utilized. Now, what is essentially guaranteed by the hardware is the fact that any application running in, say, ring 3 cannot access any data or any information present in ring 2, ring 1, or ring 0, right? In other words, or to generalize, any application running in ring I cannot access data or other information present in the rings in a lower ring, right? Now, on the RISC-V processors, we similarly have very similar to the rings. We have 3 modes of operation. So we have what is called as the machine mode, which is the most privileged. Then we have a supervisor mode, and finally the user mode, which is the least privileged, right? The supervisor mode has a privilege between the machine mode and the user mode. So typically on the RISC-V platforms, you would have your operating system running in the supervisor mode, and you would have your user applications running in the user mode. Now, very similar to the Intel scheme, any application running in the user mode cannot directly access data or any other information in the supervisor mode. Similarly, any application running in the supervisor mode cannot access data or any other information in the machine mode. So we have kind of a hierarchy of modes from the most privileged to the least privileged, right? So operating systems make use of these rings or these different modes of operations to isolate itself from the regular applications that are executing on your system, right? But we also have the second requirement, that one application should be isolated from another, right? And the way to essentially do this, or the way to essentially, or the way this is essentially achieved is with the help of what we call as virtual memory. We'll get into the details of what virtual memory is in a later class, but the essential fact is that each application is given a particular virtual memory space and is kind of sandboxed within that virtual address space. So anything it does is restricted to that virtual address space. Now, if we have each application having a different virtual address space, it means that each application or any application cannot access the code or the data of an other program which is running in a different virtual address space, right? In addition to this, we have concepts of paging, where you can set certain regions of this virtual address space as read only or read write or execute only, right? So you could have a certain region of your virtual address space which is marked as execute. What it means is that instructions that needs to be executed can be only present in this particular region, right? You could have another region of memory which is marked as read only, which means that any data present in this particular region can only be read, it cannot be modified, right. So, what we are having over here with the help of hardware is the fact that programs are given a specific virtual address space which contain its execution region, and within this virtual address space you could have various regions which are marked as execute only, read only, or read write. Yeah. So, with the increasing amount of cyber attacks that is going on these days, with the large number of such attacks due to the increasing number of systems that are essentially connected to the internet, it is critical for the operating system to also not just isolate itself and isolate processes, but also ensure that your applications are protected against external cyber attacks. So, these attacks could come in the form of viruses, worms, malware, and so on, and any such attack on your system could be essentially disastrous. So, operating systems have several aspects, very few of them are essentially detailed here, but make use of several components, or operating systems have several components such as makes use of passwords and cryptography, it has access control policies, it makes use of security assessment, biometrics, and so on to ensure the security of the system and specifically of a user's resources. So, here is an example of a very simple access control that is present on many operating systems, right. So, let us say there are 3 users, Anne, Bob, and Carl, and there are multiple programs and files that are stored on the hard disk, right. So, the operating system essentially gives assigns policies, has policies about what user, which we call as subject, can access what files. So, here for instance we have Anne, who is the owner of file 1 and can read and write to file 1, while Bob can only read to file 1, while Carl cannot access that particular file. So, this mediation about who can access what resource is essentially done by the operating system to control the access to these files, right. So, this is a very simple example of what is present, and towards the end of the course we will look into more details, get into more features of these access control policies and how an operating system is essentially utilizing these control techniques to create much more secure systems.